All right, we're going to keep with the pike theme. Next up, we're going to learn more about habitat use of juvenile northern pike with Ben Spitz.
Thank you. Hi guys, I'm Ben. I'm a master's student at SUNY ESF, and I'm going to talk to you a little bit about applying some of what Matt just talked about to look at the implications of hypoxia exposure on things like growth, condition, and habitat use of juvenile northern pike. Hypoxia is a state of low dissolved oxygen in aquatic systems, commonly defined as less than 2.0 milligrams per liter, and it's increasing in both intensity and duration across the globe. It can affect a number of things, including influencing growth, condition, maturity of fish, but also other things in the natural environment like shifting predator-prey interactions and things like habitat use. One example of a shifting predator-prey interaction that you might see is in line with the prey stress model, which says that if the prey is more sensitive to a stressor than the predator, it will be at a disadvantage and get exploited at a higher rate. So basically, in the context of hypoxia, if you have a normoxic condition, the prey might be able to evade the predator, but in hypoxic conditions, because it's more sensitive to that hypoxia, now it might get captured by that predator at a little bit of a higher rate. The effects of hypoxia are pretty difficult to study historically in situ, but more recently, elemental signatures, specifically the manganese to calcium ratio in otolith microchemistry, can provide a proxy for hypoxia exposure. This is dependent on the bioavailability of manganese in the water column. So in high oxygen conditions, it's going to be mostly present in its particulate form in the substrate, like manganese oxides. And then in normoxic conditions, it's going to be a particulate in the substrate. In hypoxic conditions, it's going to get reduced, and now it's dissolved in the water column and is bioavailable for uptake and deposition into the otolith of fishes. So while otolith microchemistry can provide us a proxy for hypoxia exposure, stable isotopes of soft tissue can allow us to infer things like trophic dynamics and habitat use. Muscle tissue is most commonly used in fisheries ecology, but it does undergo metabolic turnover, so it only represents a relatively recent time frame prior to capture. Conversely, eye lenses grow incrementally, similar to otoliths, and become metabolically inert as they form. So basically what that means for us is that if you analyze each of these discrete eye lens layers, you can recreate the isotopic history throughout the entirety of the fish's lifetime. Northern pike serve as a great species for bringing these two data sets together for a couple different reasons. For one, as we heard about earlier, northern pike generally migrate up these gradients of wetlands to spawn. When they're in these wetland habitats, after spawning in their earliest life stages, they experience really rapid growth, which should provide high-resolution data sets in both the otolith and the eye lenses. But also in these shallow wetland habitats, they're going to start to experience exposure to a lot of hypoxia. As the summer draws on, the conditions tend to get more and more hypoxic, and what we see then is these young year northern pike migrating back from these shallow wetland habitats back out to the bay where their parents came from in the first place. You can see why a fish might want to do that, because if we look at dissolved oxygen over time in both of these habitats, these wetland habitats, by June or July, they're starting to get hypoxic or even completely anoxic, and that usually continues throughout most of the summer. Conversely, over in the coastal bay or embayment habitat, it's pretty much completely normoxic throughout the entirety of the summer. Our two study sites for this project are in the upper St. Lawrence River, where coastal wetlands are heavily invaded by Typha X glauca. It creates these really dense monocultures that you see up here in the top right of this hybrid cattail. And what results from that is loading of extra organic material into the water column. As that begins to decompose, that'll suck all the oxygen out of the water and expose northern pike to more and more hypoxic conditions. In Cranberry Lake, the wetlands are pretty much completely uninvaded, and as a result, we see a lot of heterogeneity in these habitats down here in the bottom right, and pretty much normoxic conditions throughout the entirety of the summer. So that leads us to the central question: how does hypoxia exposure influence growth, condition, and habitat use of young year northern pike or juvenile northern pike in Cranberry Lake and the upper St. Lawrence River? To answer this question, what we've done so far is we've collected young year northern pike across habitats and across years using mini hoop netting, which you can see in the bottom left, and seining, which you can see in the middle. We performed otolith microchemistry with LA-ICP-MS and estimated hypoxia exposure metrics on a subset of our fish. I'll touch on that a little bit later, but we don't yet have otolith microchemistry data for all of our fish. We also analyzed northern pike muscle tissue for carbon-13 and nitrogen-15 stable isotopes. And then on to the islands processing. So this is where it gets pretty fun. So using methods developed originally by Wallace et al. 2014. Maybe it'll play, maybe it won't. I think we're frozen.
Sorry, Ben, I'm very limited technologically.
That's okay. Yeah, we're frozen. No, this is not us. Hey, that's nice.
That's a cool process.
I thought you said this was the fun part.
I think we started. Sun's not gonna float at some point. Oh, the video. They could. I've never had a problem with that before, but that's not the same. We can try it really quick and see what happens. All right, we're back. So basically this is the fun part now, I swear. This is where we peel the eye lenses under a dissecting microscope using really, really fine-tip forceps. And what you can see here is me inserting the forceps into the top of it, almost like an onion, and peeling back one layer at a time. Once I remove this layer here that you see to the left, we can dry and analyze that layer for carbon-stable isotopes. And then, after I've done this on all of my fish, we're going to develop a regression between the total eye lens diameter and the total length of the fish. So basically now what we can do is, using that regression, assign estimated total length of formation of each of these eye lens layers to that layer. So we'll have these paired data sets where we have a carbon isotope value and an estimated total length of the fish at formation. Okay, so first I'm going to look at some really, really preliminary microchemistry data that we got from a prior PhD student that let me play around with it and help develop my questions. Basically what we see here is with young year northern pike, as the duration of hypoxia exposure as provided by our manganese to calcium proxy, as that duration of hypoxia exposure increases, the growth of that fish is actually generally increasing as well. So it is a slight, but it is a significant positive relationship. There are a ton of different explanations that could be coming into play here, and I'd be happy to talk to anybody about it after this. But what I think is the most likely explanation is that in these situations, in these hypoxic conditions, these more sensitive prey taxa are now getting exploited at a higher rate, like I described a little bit in the introduction. So now basically our young year northern pike is a more efficient predator and growing more quickly because of that change in trophic interactions. Just one possibility, but I think it's the most likely and also the most exciting one to think about. Okay, now from now on we're only going to look at stable isotope data. I don't yet have any microchemistry data from any of these fish, but it is still some pretty exciting stable isotope data to talk about. So just like Matt talked about in the prior presentation, when we look at the muscle stable isotope values of these fish captured in different habitats, we see distinct separation of those habitats, which is really, really key for me. So any fish that was caught up in these wetland habitats generally has really depleted carbon-13 stable isotopes. These fish that were captured out here in this embayment generally have really enriched carbon-13 stable isotope values. However, of course, in all of ecology, it's never that cut and dry. So really what we kind of want to think about these wetlands is more of a gradient than it is two distinct habitats. So in this area circled in blue here, we have these really shallow wetland habitats. As we move down the gradient, it starts to get a little bit deeper, a little bit more open water, probably some more autochthonous production, but not really a coastal windswept embayment yet. And then we also have this windswept embayment all the way down the gradient. When we look at the carbon-13 isotope values of those fish captured in that transitional habitat, we see exactly what you would expect. So we have a gradient in the physical conditions, and we have a gradient in the isotope values. So wetland values are generally depleted. Transitional habitat is kind of moderate values in between, and then these fish that are captured out in the embayment, more enriched carbon-13 isotope values. So what that tells us is that by recreating the isotope histories through their eye lenses, what we can do is pretty much track these fish as they move down that gradient. At least that's the hope. So now we're going to look a little bit at a couple of the preliminary eye-lens stable isotope data sets that I have. So what we're looking at here on the x-axis is laminar midpoint. When all is said and done, this will be estimated total length. I'm not quite there yet with our regressions. So right now, laminar midpoint you can think of as more of a proxy for total length. So as we move right on this x-axis, that fish is getting bigger. The first thing that you notice is these fish have really enriched carbon-13 stable isotope values closer to the core, so in that really early life history. That's almost certainly maternal inputs from bay-derived resources. So if you remember, enriched carbon-13, bay-derived resources. We see that right near the core, so that's more than likely going to be maternal inputs. Then you see a really drastic depletion of our carbon-13 stable isotope. And that can almost certainly be attributed to these fish starting to feed exogenously up in these shallow wetland habitats. From there, we start to get a little bit more enriched. So that's some evidence of these fish moving back down that wetland gradient towards the bay habitats, but it's not quite as significant of a shift as I would have expected. So if a fish were to move all the way back down that wetland gradient, I would expect more of something like a U shape there. So enriched carbon isotope values from maternal inputs, depleted carbon isotope values from exogenous feeding into wetlands, and then as they move down that gradient, I would expect those values to come back up and become a little bit more enriched. Now we're going to look at Cranberry Lake, our second site. So completely different site, so forget everything you just saw about carbon isotope values. Basically what we have here are two pretty distinct habitats as well. These shallow wetland habitats where we believe they are spawning, and these more open habitats down the gradient. It's not truly a bay habitat, it's not windswept, but it's analogous to our bay habitat in the upper St. Lawrence River. And what we see here is much less separation, unfortunately, than we see in the upper St. Lawrence River. So you can see that there is some separation there, but we're talking about like a couple per mils versus like 10 to 15 per mils in the upper St. Lawrence River. So a pretty big difference here. Another thing to note is that if you remember in the upper St. Lawrence, the wetland is depleted in our carbon value. Here it's flipped. Now it's enriched relative to the bay habitat, if that makes sense. So, as you would expect, one of our first preliminary fish from Cranberry has the exact opposite trend. So we saw this U-shaped trend in upper St. Lawrence fish. Because the bay and the wetland habitat are switched in Cranberry Lake, we see the opposite trend. So although these differences are pretty slight, what this could be is maternal inputs, slightly depleted maternal inputs, some shift towards wetland habitat use, slightly enriched carbon values, and then again towards the second end of this curve, that could be our habitat shift there as those fish are moving down into those deeper bay-like habitats. So moving forward, we're looking to integrate incremental data sets from both odorless and eye lenses. What that first is going to look like is a lot of what I just talked to you about, taking these eye lens stable isotope histories and estimating when those fish changed habitats. So because odorless and eye lens both grow incrementally, we can basically overlay these two data sets. We can have an estimated total length for microchemistry data, and we can have an estimated total length for stable isotope data. So by overlaying these two data sets, we can start to assess hypoxia exposure in the early life stages of these juvenile northern pike, and then hopefully develop a relationship between hypoxia exposure in that early life stage and the timing of habitat shift. So that's going to hopefully let us answer these questions regarding how hypoxia exposure influences their habitat use and shifts throughout their early life history. So some of the conclusions that you can take from today: for one, we saw a positive relationship between growth and hypoxia exposure, potentially due to increased exploitation of prey. We saw muscle tissue stable isotope values that showed distinct separation of habitats in the upper St. Lawrence River, however, some limited separation of habitats in Cranberry Lake. And at both sites, we do see some evidence of habitat shifts occurring through their carbon stable isotope values. But we only have 3 fish total right now, so obviously we need some more. We need a higher sample size to start making some conclusions there. Some of the implications of this work: for one, native northern pike populations in the upper St. Lawrence River have been experiencing prolonged decline, so we hope that this could help identify some of the factors leading to that decline. Of course, also we hope that it informs management decisions that influence dissolved oxygen. So for one, nutrient inputs, of course, that's a classic one. Habitat enhancements and restoration that Matt talked about briefly in the prior presentation can also influence dissolved oxygen. And then even water level regulation can influence dissolved oxygen levels in the upper St. Lawrence River. So these are all management tools that hopefully we could help influence decisions regarding. And then lastly, and maybe most exciting, there's not very much literature out there right now integrating these data sets from otoliths and eye lenses. So we really hope that we can help advance this integration of these two data sets. And there are multiple data sets that you can obtain from them and multiple questions that you can answer from them. So from otoliths, you can answer things like movement and habitat use, natal origin, contaminant exposure, abiotic conditions like temperature, dissolved oxygen, salinity, metabolic condition, and obviously age and growth. Eye lenses, you can answer some of the same questions, but also add things like diet and resource use and trophic dynamics. So if we can continue to pair these two data sets, we can hopefully answer some really, really cool and exciting ecological questions. So with that, I'd like to say thank you to Thornton Ritz, the PhD student that came before me, and for providing some data, some of the microchemistry data that you saw in this presentation, to Chris Junium for helping with stable isotopes, and to Karin Lindberg for guidance regarding stable isotope analysis of eye lenses, and also, obviously, microchemistry. So with that, I'll take some questions if I have time.
We do have time for a couple questions. Yes.
How are their prey responding to the declining operative conditions?
Yeah, so we can't actually, we haven't been studying the prey itself. This is really just like a hypothesized explanation, like a shifting trophic interactions that could explain that. There are other possibilities, like the inverse relationship between dissolved oxygen and temperature, but for some reason, we have reasons to believe that that's not what's driving this relationship in this system specifically. But the belief is that potentially these prey that are smaller and have lower capacity to sustain life in hypoxic conditions are at that disadvantage like I described. But again, that's just a hypothesis. We haven't studied that yet.
Any other questions? Yes.
Have you considered looking at any other isotopes like sulfur and nitrogen for the eye lenses?
I have not, because the way that, so some of the eye lenses that I've dissected have been down to like 0.15 millimeters and like 0.005 milligrams, and to analyze those it requires, from my understanding and my experience so far, a specialized piece of equipment that Chris Junior, who was one of the people that I acknowledged on this talk, has helped me run those samples. And when you run samples that small, it gets really, really noisy when